Good day, ladies and gentlemen. Let me please introduce myself. My name is Patrik Svab, and today I would like to present the intention behind our article, the utilization of progressive methods in the manufacture and maintenance of aircraft components. It is a short content of my presentation. We'll start with the introduction and general properties, then we will go through the materials in aviation and the requirements on them. Then we will talk about potential of progressive methods in aerospace industry, and finally conclusion. Let's start with the introduction. The aerospace industry uses a wide range of materials, from metallic materials to plastics, ceramics, and composites. And when building aircraft components, the optimal properties of the material must be carefully chosen. Each material must meet all not only functional but also financial and technological requirements. And the functional properties of materials that are used in aircraft construction must be as best as possible. And the materials are chosen mainly with the lowest possible specific weight, but at the same time with a high specific strength, and so they will be able to extend the overall life cycle and lifetime of the component. And the strength characteristics of the materials are usually chosen regarding the safety as much as possible, so to the maximum possible limit. However, this means that the strength values of said material must be sufficiently reliable, and the fatigue strength properties must also not be significantly reduced during a long-term operation, and this is also associated with the overall lifetime of the aircraft. So now something about general properties. These are like the most important ones. So the main interest in the construction and maintenance of aircraft are the general properties of metals, materials and their alloys, such as hardness, malleability, flexibility, strength, density, brittleness, meltability, conductivity, contraction and expansion. There are multiple ones. So hardness refers to the ability of material to withstand wear, penetration, cutting, or permanent deformation. Hardness can be increased by cold working metals, in the case of steel and some aluminum alloys by heat treatment. The components are often made of metals in their soft state, then heat treated to strengthen them, therefore preserving their final shape. Hardness and strength are closely related properties of metals. One of the most important properties of materials is strength. Strength is the ability of material to resist deformation. It is also the property of material to withstand impact without permanent deformation, without taking much damage. And the types of loads or shocks to which the material is exposed affects its strength. Then density is the weight per unit volume of material. This is also called specific weight. And when working with aircraft, the specific weight of material per cubic inch is preferred because this information can be used to determine the weight of the part prior to actual production. Density is an important factor in selecting the material to use in the design of a part to maintain the correct weight and balance of the aircraft. Metal which can be forged, rolled, or pressed into various shapes without cracking, breaking, or leaving any other harmful phenomenon is considered to be malleable. Flexibility is a property that allows the metal to return to its original size and shape when the force that caused the shape to change is removed. This feature is extremely valuable because it would be highly undesirable to have a component that is permanently deformed after the load is removed. Each metal has a point known as the limit of elasticity, and it cannot be loaded above this value, as it would cause permanent failure, permanent damage. In the construction of an aircraft, the components and parts are designed so that their maximum load to which they are subjected does not exceed values above their limits of elasticity. And meltability is the ability of metal to become liquid when heat is applied, and conductivity is a property that allows the metal to transfer heat or electricity. Thermal conductivity of a material is especially important in welding because it regulates the amount of heat that will be needed for proper melting. Conductivity of the metal to some extent determines the type of preparation which should be used to control expansion and contraction of the material. Now, materials in aviation. Many materials have been used in the history of aviation. In the beginning, mainly wood and fabric. Then later aluminium and multiple specific alloys were used. Alloys have a general representation in aviation to this day, as the alloys have required properties for the individual elements of the aircraft structure and construction in general. Over the years, and with the gradual development in aviation and aircraft construction, development has reached an important milestone: composite materials. Composite materials are modern materials, and the development of which began not so long ago. Even though their construction itself was observed, to be honest, from nature. Among composite materials with fibrous structure, we also include wood for its structure, also bamboo, grass blades, or the structure of animal bones. Composite materials are divided according to their type of reinforced component into composites that are reinforced with fibers or short fibers, so-called whiskers, and composites that are reinforced with dispersion, for example, metal oxides, and composites produced by controlled crystallization. Composites are further divided according to the type of matrix into composites with organic matrix, or polymers, ceramic, and metal. The last group consists of composites formed by a silicate matrix, for example, prestressed concrete or reinforced concrete, which are often used in construction. Depending on these resulting properties, composites are divided into composites that have high mechanical properties and composites that have special physical-chemical properties. Imported composite is Aral. It was the first fiber metal laminate used in aerospace. It was invented in 1978 in laboratories designed for material research in the Netherlands. After considering the use of the newly formed composite materials, it was found after evaluations in flight simulation that by using Aral, the weight of aircraft can be reduced by up to 30% and their service life can be significantly extended. Due to its excellent fatigue resistance, Aral began to be used mainly on the lower parts of the wings for covers and rear rudders. But Aral cannot be made with fibers that are oriented in multiple directions. These problems were fundamental as they limited the laminate properties and thus its use in places where it is subjected to high stresses. Instead of aramid fibers, glass fibers were first used and applied in laminate in 1990s. And this laminate was called glare, and so many negative aspects, many problems that Aral had. In addition, it surpassed its many mechanical properties. So glare could finally be processed with the orientation of the fibers in multiple directions. This allowed the designers to use this laminate in much larger proportions of structures and aircraft constructions. In the picture, we can see Boeing 747. As you can see, it consists by 50% of composites. So requirements on materials in aerospace industry, there are many of them. You can see the most valuable, most important ones. And there are certain basic requirements for materials. These requirements, due to their high energy consumption, are high strength at low weight and resistant to stress. Also resistant to atmospheric conditions and to permanent damage. These conditions include the atmospheric conditions include rain, hail, icing, atmospheric discharges, heat stress, sunlight, or for example also bursts are considered atmospheric conditions. In particular, the strength requirements are formulated by aeronautical regulations to minimize the likelihood of failures due to the lower value of the strength characteristics of the material than those taken into account in the, for example, design calculations. So load resistance, if either dynamic or static tests are used to demonstrate compliance with the airworthiness regulations, factors suitable for repair shall be used to correct the test results depending on the construction materials that are used that are tested. Suitability as well as durability of the materials used for the production of components, the failure of which may adversely affect safety, overall safety, is assessed on the basis of demonstrable tests and experience. This corresponds to the approved standards which are consistently applied. Is the technical regulations of military and civil aviation specifications that ensure that the actual load-bearing characteristics of the structure as well as other properties will be in accordance with the design data from the pre-construction calculations and simulations. So in addition, all probable environmental influences such as humidity or temperature that can be expected when operating aircraft must be taken into consideration, must be considered. The strength characteristic of the material must be documented by the required quantity and in the required quality of the performed test processed by means of statistical methods. Important property in the requirement: fire resistance. Flammable liquids and vapors must be defined and identified in detail from each area of their possible escape. Parts of the, for example, engine installation, the basic control system, and also parts of the primary structure, which occur in area where leakage of liquids is possible, and these liquids are flammable, or in areas which are adjacent and could therefore be exposed to direct fire. These areas must be manufactured from fire-resistant construction material or must be shaded in such way so they will be able to withstand fire and its effect. Now, the potential of progressive methods in aerospace industry. In a matter of construction, when regarding the construction and like aviation industry, in terms of construction of the aircraft, additive manufacturing (AM) can be defined as the exact opposite of traditional machines to produce parts of or components. As you can see in the picture, case A is called subtractive manufacturing, when you have the whole material and then you manufacture the part or desired shape from that material, which produce much more waste than additive manufacturing. Additive manufacturing is, for example, 3D printing, but in nowadays conditions, which are greatly increased in the overall characteristics and properties of the material. So several additive manufacturing techniques have been introduced in recent years. And what makes AM interesting is that thanks to the maximum freedom in shaping, it is possible to create even extremely complex shapes and complex structures based on thin lattice structures can achieve high structural efficiency, where the whole material exhibits similar stress values at all points. Industry 4.0 concept introduces several key assistive technologies that could change aircraft maintenance. One of them is also augmented reality. Technologies such as additive manufacturing and augmented reality, which have been improved by the industry 4.0 revolution, will be a key element in the aviation maintenance strategies of the future. It should be noted that the aircrafts, helicopters, and other automatic machines can be composed of million parts, and they require complicated maintenance. which often require specific equipment and tools needed for assembly or disassembly. In this place, virtual reality can be useful in these areas of advanced engineering, where it is possible to undergo virtual training and practice precise procedures in various situations that reduce the occurrence of human errors due to incorrect placement and use of incorrect type or parts. Realistic 3D CAD model of the part that needs to be maintained can be projected into video stream where an external organization such as technician specializing in these types of failures can also comment on the problem. Training in virtual reality where the scenario moves forward only if the set conditions are met can help reduce the risk of skipping a phase or step in a maintenance process, which can really very easily occur in a real situation. Additive manufacturing can be also combined with AR or VR. In fact, virtual reality can be useful for creating an extended maintenance manual and illustrated parts catalogs, where the appearance of the part being repaired is designed by the operator intuitively based on the actual aircraft. This is especially true for VR and AR-based manuals, where assembly and disassembly tasks are presented to operators through a combination of CAD models, symbols that suggest manual operations, virtual panels where operations can be controlled, and communicate with technology through gesture tracking. Additive manufacturing could also be used for remote maintenance, where virtual animations could be prepared in real time to support and manage complex procedures through centralized maintenance centers, and if necessary, the captured image will be projected to remote operator and to remote devices. This could overcome one of the problems that currently limits the use of VR in industry, and it's the time needed to prepare animations. In the case of modern transport, aircraft is made of many parts. It should be noted that the implementation of the animated virtual sequences for each possible maintenance operation would be time consuming, but in a greater picture it will be very useful and you can say efficient. So in conclusion, the ability of augmented reality and virtual reality to combine virtual and real parts allows you to simulate complex scenarios without the need of inaccessible parts. Overall, the impact of virtual reality of aircraft maintenance can be really big, really huge, especially in dealing with complex operations that cannot be clearly explained in traditional paper manuals. In addition, the documentation must be in operation for several decades, with the average service life of commercial aircraft ranging from 20 to 40 years. Virtual reality can help to update maintenance procedures for instructions based on text or real-time maintenance documents. However, implementing all commercial aircraft maintenance tasks in virtual reality can be and is a complex task. Nowadays, the most realistic solution is to design the initial implementation of only the most critical, the most crucial and demanding maintenance operations in the VR. On the integration of short-term maintenance preparation environments and enrich scenes into the virtual reality system using CAD modeling, using CAD modeling could reduce the time required to implement entire maintenance manual in virtual environments in the near future. Virtual reality can be used in aviation to support maintenance in several ways. Illustrated augmented reality or virtual reality based parts catalogs, virtual environment based maintenance manuals, remote maintenance software tools, VR support assembly and disassembly operations. These are just one of the many solutions this technology provides and can provide that can benefit from implementation. And eventually, this method to aviation industry. This technology, the virtual reality, can be useful for bridging the gap between traditional text manual training, where simplified two-dimensional sketches represent complex components and the reality where complex three-dimensional shapes must be detected and assembled, often hidden under other components and assembled or disassembled using advanced technology tools. These are just like main problems that can be focused on in the future. So that will be all from my presentation. Thank you for your attention. I hope you enjoyed it. If in case of any questions, feel free to ask or contact me.